have you ever just looked around and wondered what holds the world together? I mean, everything from the salt on your fries to the water in your glass, it's all connected by these invisible forces. So today, we're going to play detective and uncover the secret glue of the universe, chemical bonds. Let's start with our first clue. You know, every good detective story needs a central mystery. And ours? Well, it begins with a simple puzzle that I guarantee you've seen in your own kitchen, probably sitting right there in a bottle of salad dressing. You can shake it, you can stir it, you can do whatever you want to it, but no matter what, it just separates. Every single time. Why does it do that? This simple, everyday thing is actually our first big clue. And to find the answer, we have to go from the kitchen all the way down to the microscopic world of atoms. To crack this case, we've got to shrink down. I mean, way, way down. The real answer isn't in the oil or the water as a whole. It's in the tiny, fundamental forces that hold their basic building blocks, their atoms, together. So it's time to meet our main suspects. These are the chemical bonds, the very forces responsible for how all atoms interact with each other. They're the reason some things stick together like glue, and others, well, like our oil and water, want nothing to do with each other. So what even is a bond really? At its heart, think of it as a fundamental force of attraction. It's the invisible glue that holds individual atoms together, letting them form all the stable stuff we see and touch every day. Okay, so down at the atomic level, atoms have two main strategies for connecting. Sometimes it's a complete transfer of electrons. One atom literally gives one away, and another one takes it. Other times, it's more of a team effort where they decide to share electrons. And these two different strategies create two very different kinds of bonds. So let's put our two primary suspects, ionic and covalent bonds, right under the spotlight. If we can understand how they operate, we get a whole lot closer to solving our oil and water mystery. First up, we have ionic bonds. And you can think of these as the ultimate transaction. They form when one atom completely gives away an electron and another atom swoops in and takes it. It's a clear-cut deal. So here's the deal. Metals, they tend to lose electrons, which makes them positively charged ions we call cations. Nonmetals, on the other hand, gain those electrons, becoming negative anions. And as we all know, opposites attract. That positive cation and that negative anion are then held together by a super strong electrostatic force. And hey, here's a fun way to remember it. A cation is positive. And this whole give and take relationship, it leads to some pretty distinct properties. Ionic compounds, like your table salt, form these really rigid, crystalline solids. They're super tough to melt, but they're also surprisingly brittle. Let's see why that is. This is a brilliant way to see that brittleness in action. So in a perfect crystal, you have positive and negative ions all lined up perfectly. But if you hit it with an external force, like a hammer, you shift those layers just a bit. And suddenly you get positive next to positive and negative next to negative. They repel each other like crazy, and the whole crystal just shatters. All right, let's move on to our other suspect, covalent bonds. Now, if ionic bonds are all about giving and taking, covalent bonds are all about sharing. This is what happens between nonmetal atoms that figure out it's way better to share electrons to become stable, instead of just transferring them completely. Okay, let's put them head to head. Ionic bonds, they're all about transferring electrons, usually between metals and nonmetals. This creates those strong, brittle crystals with really high melting points. Covalent bonds, on the other hand, are about sharing electrons between nonmetals. This forms these little individual units called molecules, which are often liquids or gases with much, much lower melting points. You can see they have two totally different personalities. Okay, so we've met our bonds. But how does any of this get us back to our salad dressing? Well, here comes the plot twist. It turns out that when it comes to covalent bonds, that whole sharing thing, it isn't always equal. And this, right here, is the key to cracking the whole case. This brings us to a really crucial concept, the polar bond. This is a special kind of covalent bond where the shared electrons actually spend more time hanging out around one atom than the other. I mean, it's still sharing, but it's, a lopsided deal. Honestly, the best way to picture this is as a microscopic tug of war. Some atoms are just naturally stronger. We call this being more electronegative, and they just pull those shared electrons a little closer to their side. Here's a perfect example.
In the electron tug of war, fluorine is an absolute heavyweight. It yanks those shared electrons away from hydrogen, creating a slight negative charge on the fluorine side and a slight positive charge on the hydrogen side. And that little arrow you see, that's called a dipole arrow, and it shows you exactly which way the electrons are being pulled. Now, let's look at a molecule we all know and love, water. The oxygen atom is way stronger than the hydrogen atoms, so it pulls their electrons in. And because of water's cool, bent shape, those two poles don't cancel each other out. This gives the entire water molecule a slightly negative side and a slightly positive side. It's a polar molecule. And here it is, the final piece of evidence we need to solve the case. Oils? They're made of non-polar molecules. In these long chains, the electrons are shared much more evenly. There aren't any positive or negative ends because, in that atomic tug of war, it's pretty much a tie. So, with all the evidence gathered, we can finally reveal the fundamental law that solves our mystery. It's a simple but incredibly powerful rule in chemistry: like dissolves like. And that's it. That's the solution. The polar water molecules, with their positive and negative ends, are super attracted to each other. The nonpolar oil molecules, they're perfectly happy sticking together too. But the two groups, they just aren't interested in mixing. It's kind of like two different crowds at a party that just refuse to mingle. The attraction of water for itself is just way stronger than its attraction for oil. Case closed. So we've solved the case of the separating salad dressing, but let's just step back for a second. This tiny, invisible tug of war over electrons isn't just some weird kitchen curiosity. It has absolutely massive implications for our entire world. You see, the very same polarity that makes water refuse to mix with oil is also what allows it to dissolve things like salt and sugar and countless other substances. It's the reason we call water the universal solvent. This one property is fundamental to our weather, our geology, and most importantly, the chemistry going on inside every single living cell on this planet. Life as we know it literally depends on this principle. So the next time you see oil and water separating, you'll know you're not just looking at salad dressing. You're actually watching a fundamental law of the universe play out in real time. And it kind of makes you wonder, if these tiny little bonds have such a massive impact, what other invisible forces are out there quietly shaping the world right in front of your eyes?